Imagine if the vast majority of something really fundamental to our universe just wasn't there. I mean, not in a way we can see.
Right. Completely invisible.
Untouchable, utterly unknown to us directly. It sounds like something straight out of science fiction, doesn't it?
It really does.
But it's not. It's actually one of the biggest puzzles in astrophysics today.
Absolutely.
And that's what we're diving into today. The Enigma of Dark Matter. You've probably heard the phrase bounced around, but what does it really mean when scientists talk about dark matter?
That's exactly it. We're tackling what is, well, arguably one of the greatest scientific mysteries of our time. This whole enigma of dark matter thing.
Yeah.
It's a substance that sort of quietly but really profoundly shapes entire galaxies, the whole fabric of space, all while hiding in plain sight. It's a concept that doesn't just challenge our understanding. It pretty much revolutionizes how we think about what the universe is actually made of.
Right. It forces you to confront the fact that what we see, what we perceive directly, is just a tiny, tiny fraction of what's really out there.
Exactly. A very humbling fraction.
So our mission today, it's pretty straightforward, but ambitious too. We want to unpack exactly what dark matter is.
What the science says it is, yeah.
Why are scientists so convinced it exists, even though we can't see it? That's a big one.
Crucial.
Yeah.
The evidence is key.
And what do they think it might actually be made of? What are the candidates?
The big suspects, yeah.
And maybe the most exciting part for me, how are they actually trying to find it, like physically detect this stuff?
The hunt. It's a fascinating story of ingenuity.
We're going to peel back the layers of this cosmic riddle, drawing on, the latest understanding, the core ideas, to try and shine a light, ironically, on this invisible component of the cosmos.
And our goal for you, listening in, is to give you more than just the surface stuff. We want you to have those aha moments.
Yeah.
A quick, but hopefully pretty thorough grasp of one of the universe's most mind-bending unsolved puzzles. We want you walking away not just knowing what dark matter is, but really getting why it matters.
And appreciating the detective work involved.
Oh, absolutely. The sheer cleverness of figuring out something so hidden is amazing.
Definitely. So whether you're just, super curious about the cosmos, or maybe you're trying to make sense of the latest astrophysics news.
Or maybe you've got a meeting where this might come up, who knows?
Right. Our goal is to cut through the jargon, give you those core insights without the information overload. So let's start this journey. Let's try and understand this invisible giant.
Let's do it.
Okay, let's unpack this. The name itself, dark matter, tells you something's hidden. But when we say invisible, what does that really mean? How does it interact, or rather not interact?
That's the absolute core of it. It's a fundamental paradox.
Yeah, how can something be so important, shape everything, yet we can't see it, can't touch it? Our best instruments just draw a blank.
It is paradoxical. So fundamentally, dark matter is defined as this, well, mysterious, invisible substance. We know it's there because it exerts gravity. It pulls on this. We can see the stars, the galaxies, the gas.
Okay, so gravity is the key. It has mass, it has gravity.
Exactly. But, and this is the crucial part, why we call it dark, it doesn't seem to interact with light at all. Meaning it doesn't emit light like a star. It doesn't absorb light like dust. And it doesn't reflect light like a planet or a mirror. It's completely transparent to all forms of electromagnetic radiation.
So the entire spectrum, radio waves, microwaves, infrared, visible light, UV, X-rays, gamma rays, it just ignores all of it.
That's the idea.
Yeah.
Ordinary matter, everything we know and are made of, interacts with that spectrum in some way. That's how we detect it, see it, measure it. Dark matter, it seems to be completely aloof to all of that.
So it's not like a black hole then, because black holes are dark because light can't escape their gravity.
Exactly. That's a great distinction. Black holes are dark due to overwhelming gravity-trapping light. Dark matter is dark because it seems to be fundamentally indifferent to light. It just doesn't participate in those electromagnetic interactions.
Wow. Okay, so undetectable by conventional means really means it's something fundamentally new, isn't it? Something outside our standard picture of particles and forces.
That's precisely the implication. It's like trying to understand, I don't know, a complex engine, but maybe 85% or even 95% of its working parts are completely invisible to you.
You can see the gears turning, you hear the engine running, you feel the vibration, you know the parts are there doing something.
Right. You see the effects. You know they must be there. But the parts themselves, you can't lay eyes on them.
That really drives home the challenge. It's total lack of interaction with light and presumably most other forces that ordinary matter feels. That's what makes it so slippery.
Completely. We are totally reliant on its gravitational fingerprint. That's our only real window into its existence and its behavior.
So if a lump of dark matter, whatever that looks like, flew right through this room, right through us, we're
We'd
good.
feel a thing, not a flicker. It would pass through the atoms in your body, the walls, the earth, pretty much unimpeded, like a ghost, basically.
Which is, incredibly frustrating if you're trying to build a detector for it.
Absolutely. And also, yeah, a bit humbling. It reminds us how limited our everyday senses are in grasping the full picture of reality.
Okay, so it's ghostly, interacts only via gravity. But how much of this stuff are we actually talking about? Is it like a minor fringe component of the universe, or is it a major player?
Oh, it's a major player, a dominant one, in fact. Our best estimates, and these come from combining lots of different kinds of observations.
Like what?
Things like the cosmic microwave background, the way galaxies cluster together, gravitational lensing, the way galaxies rotate, putting all that data together.
Okay.
The picture that emerges is that dark matter makes up roughly 27% of the total mass energy content of the universe.
27%. Okay, how does that compare to, well, us, ordinary matter?
That's where it gets really mind-blowing. Ordinary visible matter, everything we can see and touch, all the stars, planets, gas, dust, every atom in you and me, everything ever observed directly, that only makes up about 5% of the universe's total budget.
5%, only 5.
Only 5%. So dark matter outweighs all the normal stuff by more than 5 to 1.
Whoa.
The sheer dominance of this unseen component is it's staggering. Think of an iceberg. We know most of it's underwater. But imagine if the underwater part wasn't just hidden, but made of some completely different invisible kind of ice we didn't even know existed. That's
Yep.
sort of the situation.
Okay, that really puts it in perspective. Less than 5% is the familiar universe, all the stars and galaxies we see in Hubble images. And the rest, well, 27% is this dark matter. And then there's something else too, right? Dark energy.
Exactly. The remaining 68% or so is thought to be dark energy, which is even more mysterious in some ways, driving the universe's accelerated expansion. But focusing on the matter side, yeah, 27% dark matter, 5% ordinary matter.
This just fundamentally shifts your perspective on the cosmos, doesn't it? If most of the matter out there is something we can't detect directly.
It absolutely does. It forces us to rewrite the cosmic recipe book. For centuries, physics built its understanding on the matter and energy we could observe and interact with. Now, we're faced with the undeniable evidence that our inventory, our periodic table of fundamental particles and forces, is seriously incomplete.
So the standard model of particle physics, it doesn't include dark matter.
Not in its current form, no. The standard model is incredibly successful at describing the 5%, the quarks, leptons, photons, gluons, W and Z bosons, the Higgs. But dark matter seems to lie entirely outside of that framework.
Which means finding it would be revolutionary.
Oh, completely. Nobel Prize territory. Easily. It would open up a whole new sector of fundamental physics. It implies the cosmic stage is dominated by actors we can't see, yet they're directing the play. It's a profound cosmic modesty lesson.
And this huge chunk of invisible matter, this 27%, it's not just sitting there, is it? You said it shapes things. What does it do? What's its big role in the universe?
Its role is absolutely fundamental. You could call it the cosmic architect, or maybe the universe's invisible scaffolding. Dark matter's gravity influences the formation and structure of basically everything large-scale we see.
Like galaxies.
Galaxies, definitely. But also galaxy clusters, these huge collections of hundreds or thousands of galaxies all bound together. And even the largest structures we know of, the cosmic web.
Okay, tell me more about the cosmic web. That sounds fascinating.
It is. Imagine the universe isn't just galaxies scattered randomly. On the largest scales, it looks more like a sponge or a network.
Yeah.
There are vast, almost empty regions called voids, and connecting everything are these long, thin filaments made of galaxies and gas, and denser regions where these filaments intersect. Those are the galaxy clusters.
Like a giant interconnected structure across billions of light years.
Precisely. And the formation of this entire cosmic web, the filaments, the voids, the clusters, it's driven primarily by the gravity of dark matter.
So without dark matter, this whole structure wouldn't exist. Or it would look totally different.
It almost certainly wouldn't exist in the way we see it. The ordinary matter, the 5% we see, simply doesn't provide enough gravity on its own to clump together efficiently and form these vast structures against the expansion of the universe, especially early on.
Why not? What's special about dark matter's gravity?
Well, partly it's just that there's so much more of it. But also, crucially, dark matter doesn't interact with light. Ordinary matter, like gas, feels pressure from radiation, it heats up, it radiates energy away. This complicates how it collapses under gravity. Dark matter doesn't have those problems.
Ah, okay, so it can start clumping earlier and more effectively.
Exactly. Dark matter started clumping together very early in the universe's history, forming these invisible gravitational wells, or halos. These halos then acted as gravitational seeds. Ordinary matter, the gas that would eventually form stars and galaxies, was naturally drawn into these pre-existing dark matter structures.
So the dark matter forms the mold, and the ordinary matter flows into it.
That's a perfect analogy. It provides the gravitational backbone, the scaffolding upon which the visible universe is built. Without that initial dark matter structure, the small density fluctuations in the early universe likely wouldn't have grown into the galaxies and clusters we see today. The universe would be much more uniform, much less structured.
It's really incredible to think about, something invisible orchestrating the grandest structures we know.
It is. It dictates where galaxies form, how they cluster, and even how they spin.
Okay, that brings us right back to the evidence. If we can't see it, touch it, interact with it electromagnetically, how on earth do we know it's there? You mentioned its gravity, but what are the specific clues, the smoking guns?
Right. It's all about following the gravitational breadcrumbs. Its presence is entirely inferred, like cosmic detective work. But the key thing is, we have multiple independent lines of evidence, all pointing to the same conclusion. There's a lot more mass out there than we can see.
It's not just one weird observation, then.
No, absolutely not. If it were just one thing, scientists would be much more skeptical. But we see its effects on the scale of individual galaxies, on the scale of galaxy clusters, and even on the scale of the entire observable universe, going back almost to the Big Bang.
Okay, let's break those down. You mentioned how galaxies spin. Let's start there. That seems like one of the earliest, really compelling pieces of evidence, right? The whole galaxy rotation curves thing.
Yes, that's a classic. The puzzle really started gaining traction back in the 1970s, mainly thanks to the incredibly careful work of astronomer Vera Rubin and her colleague Kent Ford. Though Fitzwicki had noted similar issues in galaxy clusters way back in the 30s.
And what was Vera Rubin looking at?
She was meticulously measuring the speeds of stars orbiting the centers of spiral galaxies like our own Milky Way or Andromeda. Now think about our solar system. Mercury, close to the sun, orbits really fast. Neptune, way out, orbits much more slowly.
Because the sun's gravity gets the farther out you go. Kepler's laws, right?
Exactly. You'd expect the same basic principle in a galaxy. Most of the visible light, and therefore presumably most of the visible mass, the stars, gas, dust, is concentrated towards the center. So based on that visible matter, you'd expect stars farther out from the galactic center to orbit much more slowly than stars closer in. Their speeds should drop off with distance.
Makes sense. You map out the light, figure out the mass, predict the orbital speeds, but that's not what she found.
Not at all. That's what was so revolutionary. Rubin and Ford's observations across many galaxies showed something completely unexpected. The stars in the outer regions of these spiral galaxies were moving just as fast, sometimes even slightly faster, than the stars closer to the center.
They weren't slowing down. The rotation curve stayed flat instead of dipping.
Precisely. The rotation curve, which plots orbital speed against distance from the center, was expected to fall off, but instead it stayed stubbornly flat, or even rose slightly, far out beyond the visible edge of the galaxy.
What does that imply? How do you keep stars moving that fast so far out?
It implies there has to be a lot more gravity holding them in orbit than the visible matter alone can provide. To keep those outer stars whipping around at such high speeds without flying off into intergalactic space, there must be a significant amount of unseen mass exerting a strong gravitational pull.
Unseen mass. Dark matter.
Exactly. This was a huge discrepancy. The observations demanded much more mass than could be accounted for by stars and gas. The implication was unavoidable. Galaxies must be embedded within massive, invisible halos of dark matter, extending far beyond their luminous boundaries.
So the visible galaxy is just the tip of the iceberg, sitting inside a much larger dark matter structure.
That's the picture that emerged. This flat rotation curve observation was one of the first really solid, undeniable pieces of evidence that forced astronomers to take the idea of dark matter seriously. It was a foundational aha moment. Vera Rubin's careful work really cemented it.
Okay, that's incredibly compelling. Fast-spinning galaxies point to unseen mass. What's another major clue? You mentioned light bending.
Right. Gravitational lensing. This is another powerful tool based on Einstein's theory of general relativity.
Which says that mass warps space-time, right?
Exactly. And light travels through space-time. So if space-time is warped by a massive object, the path of light passing nearby will be bent. It's like how a lens bends light, but in this case, the lens is gravity itself.
So really massive things in space can act like lenses.
Yes, incredibly massive objects, especially huge galaxy clusters. Remember, those collections of hundreds or thousands of galaxies that contain so much mass that they significantly warp space-time around them. They act as giant natural cosmic telescopes or magnifying glasses.
What happens to light from objects behind them?
Light from even more distant galaxies, located far behind the cluster, has to pass through this warped spacetime on its way to us. Its path gets bent. From our perspective on Earth, this can make the background galaxies look distorted.
Distorted how?
We might see them stretched to arcs, or magnified, or even see multiple images of the same background galaxy appearing around the foreground cluster. Sometimes you get these beautiful patterns called Einstein rings or crosses.
Like looking through the bottom of a wine glass, maybe? You see weird shapes?
That's a good analogy. The key point for dark matter is this. The amount of bending, the degree of distortion we observe, depends directly on the total amount of mass in the foreground lensing object, the cluster, in this case.
Total mass meaning visible and invisible.
Precisely. It doesn't matter if the mass is shining or dark. Gravity cares about mass, period. So astronomers can use powerful telescopes like Hubble to carefully measure these lensing distortions around galaxy clusters. They map out how much the light is being bent.
And what do they find when they compare the required mass to the visible mass?
They consistently find that the amount of gravitational lensing observed is far greater than what could be produced by the visible matter alone. All the stars in the galaxies, all the hot gas we see with X-ray telescopes. Again, there's a huge discrepancy.
So just like with the spinning galaxies, the bending of light is telling us there's much more mass there than meets the eye.
Exactly. To explain the observed amount of lensing, you need a lot more mass distributed throughout the cluster, often in a smoother way than the clumpy visible galaxies. This perfectly matches the idea of vast amounts of dark matter permeating the cluster. It's like we're directly weighing the cluster using gravity itself and finding it's much heavier than it looks.
That feels like very direct evidence, even though we're not seeing the dark matter itself. We're seeing its gravitational effect on light.
It's one of the most powerful confirmations we have. You can literally make maps of where the mass must be based on the lensing and compare them to maps of where the light is. They don't line up without adding a huge component of dark matter.
Okay, so galaxies spinning too fast, light bending too much around clusters. You also mentioned evidence from the very early universe, something about its baby picture.
Yes, the cosmic microwave background, or CMB. This is truly fundamental evidence coming from a completely different era and scale of the universe.
Remind us what the CMB is again.
The CMB is essentially the oldest light in the universe, the leftover heat from the Big Bang. It's like an afterglow. It comes from a time when the universe was only about 380,000 years old, incredibly young in cosmic terms. Before that, the universe was so hot and dense that it was opaque, like a thick fog.
And then it cooled enough for atoms to form and light could travel freely.
Exactly. The universe became transparent, and that light, released then, has been traveling across space ever since, cooling and stretching as the universe expanded. Today, we detect it as a faint glow of microwave radiation coming from all directions.
And it's almost perfectly uniform, but not quite.
That's the crucial part. It's incredibly uniform, but there are tiny, tiny variations in temperature, like differences of only a few parts per 100,000 from one spot in the sky to another. These anisotropies, these slight temperature fluctuations, are incredibly important.
Why? What do they represent?
They represent tiny variations in the density of matter and energy in the very early universe. Think of them as the primordial seeds from which all the structures we see today, galaxies, clusters, the cosmic web, eventually grew over billions of years. Denser regions eventually collapsed under gravity to form structures, while less dense regions became voids.
Okay, so how does dark matter fit into this picture of the CMB?
The precise pattern of these hot and cold spots in CMB, their size, their distribution, how strong the fluctuations are at different scales, this pattern is incredibly sensitive to the ingredients of the early universe. Specifically, it depends very strongly on the amounts of ordinary matter, dark matter, and dark energy present back then.
So you can model the universe with different recipes and see which one matches the CMB picture we observed.
Exactly that. Cosmologists run complex computer simulations of the early universe with different amounts of dark matter and ordinary matter. What they find is that the observed pattern of fluctuations in the CMB, particularly the relative heights of the peaks in its power spectrum, which is like a statistical fingerprint of the CMB, can only be accurately matched if the universe contains roughly 5 to 6 times more dark matter than ordinary matter.
So the CMB itself tells us the ratio had to be about 27% dark matter to 5% ordinary matter, way back then.
Yes, the fit is remarkably precise. Without dark matter, the model simply doesn't work. The ordinary matter alone wouldn't have had enough gravitational pull to overcome the radiation pressure in the early universe and allow those initial density seeds to grow as efficiently as they needed to, forming the structures we see today.
Why wouldn't ordinary matter be enough?
Because ordinary matter interacts strongly with light photons. In the hot, dense early universe, this interaction created a lot of pressure that resisted gravitational collapse. Dark matter, being dark, didn't feel this pressure. It could start clumping gravitationally much earlier, providing those essential gravitational wells that pulled in the ordinary matter once the universe cooled enough.
So again, it's the gravitational scaffolding, but this time right at the beginning, enabling structure formation.
Precisely. The CMB provides incredibly strong evidence that dark matter isn't just something affecting galaxies today. It was a crucial component from the universe's infancy, fundamentally shaping its evolution from the start. It ties the whole picture together across cosmic time.
Wow, okay, galaxy rotation, gravitational lensing, the CMB. That's a pretty compelling trifecta of evidence from a very different scales and epochs.
And there are other lines of evidence, too, like the large-scale distribution of galaxies, observations of colliding galaxy clusters like the Bullet Cluster. They all point consistently toward the existence of this unseen mass.
It seems undeniable that it's there. Which brings us to the absolute core question. What is it? What is this stuff actually made of?
That is the million-dollar question.
Yeah.
Or maybe the billion-dollar question. It's the ultimate prize right now in particle physics and cosmology. And the simple, honest answer is, despite decades of intense research, we still don't know for sure.
Oh, really? After all that evidence showing it exists?
Yep. Its composition remains a complete mystery. We have very strong indirect evidence that it exists and what it does gravitationally, but its fundamental nature, the actual particle or particles involved,
Yeah.
that's still elusive. We have some promising ideas, some leading candidates, but no definitive proof yet.
It's like knowing a crime was committed, having fingerprints, witness accounts of the effects, but not knowing who the culprit actually is.
That's a perfect analogy. We have the fingerprints all over the cosmos, but we haven't caught the particle red-handed yet.
Okay, so let's get into the suspects. What are the leading candidates? For a long time, the main contender seemed to be something called a WIMP brain.
Yes, WIMPs were, and arguably still are, a major focus. WIMP stands for Weakly Interacting Massive Particle.
Okay, break that down. Massive.
Massive means they're expected to have a significant mass, perhaps somewhere between a few times and maybe 1,000 times the mass of a proton. This mass is needed to provide the gravitational effects we observe. They're not massless like photons.
Got it. And weakly interacting. That sounds key.
That's the crucial part for explaining their behavior. Weakly interacting means they interact with other particles primarily through gravity and possibly the weak nuclear force, but not through the electromagnetic force or the strong nuclear force.
Not interacting electromagnetically. That's why they're dark, right? No light interaction.
Exactly. No emission, absorption, or reflection of light. And not interacting via the strong nuclear force means they don't clump together inside atomic nuclei like protons and neutrons do.
And interacting only weakly means they mostly just pass through ordinary matter.
Precisely. The weak interaction is very short range and, well, weak. So a WIMP would only very rarely bump into the nucleus of an ordinary atom. Most of the time, they'd fly right through us, the Earth, everything, without leaving a trace. This explains why they are so hard to detect directly.
And why don't they clump together like ordinary matter does to form, say, dark matter stars or planets?
That also comes down to their interactions. Ordinary matter can cool down and collapse into dense objects because its particles, atoms, ions, can easily collide with each other and, crucially, radiate away energy, mostly through electromagnetic interactions that glow, essentially. Losing energy allows them to fall deeper into gravitational wells and condense.
Okay.
WIMPs, interacting only weakly, wouldn't collide often, and even if they did, they wouldn't have an efficient way to radiate energy away. They can't cool down in the same way. So instead of collapsing into dense objects, they tend to form vast, diffuse, roughly spherical halos around galaxies.
So their weak interactions lead directly to these giant, spread-out halos that the rotation curves suggested.
Exactly. The properties hypothesized for WIMPs naturally lead to the kind of large-scale structures we infer from observations. There was also a theoretical bonus called the WIMP miracle.
The WIMP miracle? What's that?
It's a neat coincidence. If you assume a new particle exists with a mass roughly 100 times the proton mass, and it interacts via the weak force, typical strength, Calculations show that these particles would have been produced in the Big Bang in just the right abundance to match the amount of dark matter we observe today, around 27%.
So the theory predicted the right amount automatically.
Kind of, yeah. It seemed almost too good to be true. A particle motivated by solving the dark matter problem naturally had the right cosmological abundance if it interacted via the known weak force. This made WIMPs a very attractive candidate for a long time.
But we still haven't found them. Are there other contenders? What if it's not WIMPs?
Absolutely. As experiments searching for WIMPs have come up empty, enthusiasm has grown for other possibilities. Another very well-motivated candidate is the axion.
Axions. Are they similar to WIMPs?
Not really. Axions are predicted to be extremely light particles, much, much lighter than electrons, let alone protons or typical WIMPs. They were originally proposed back in the 70s to solve a completely different problem in particle physics related to the strong nuclear force, called the strong CP problem.
So they weren't invented just for dark matter?
No, they have independent theoretical motivation. It turns out that if axions exist, under certain conditions, they could also have been produced in the early universe in vast numbers, and because they are so light and interact so weakly, they could collectively make up the dark matter.
How would you even detect something so light and weakly interacting?
It requires completely different experimental techniques than WIMP searches. Axion experiments often involve very strong magnetic fields, trying to coax axions to convert into detectable photons, light particles. It's a very challenging hunt as well. Examples include experiments like ADMX.
So WIMPs, axions, any other exotic ideas out there?
Oh, plenty. The theoretical landscape is rich. Some people explore the possibility of sterile neutrinos, which are hypothetical heavier cousins of the known neutrinos that interact only via gravity. Others look at more complex hidden sector theories, where dark matter might have its own set of particles and forces that barely interact with our standard model world. There are ideas like fuzzy dark matter, where the particles are so incredibly light they behave more like waves on galactic scales, and some even reconsidered primordial black holes formed in the very early universe, though constraints make that difficult for them to be all of the dark matter.
And all these candidates, WIMPs, axions, sterile neutrinos, they are all outside the standard model of particle physics.
Yes, that's the crucial link. The standard model, our incredibly successful theory of ordinary matter and forces, simply doesn't contain a suitable dark matter particle. It has neutrinos, but they're too light and fast-moving to account for the cold dark matter structures we see.
So finding dark matter isn't just solving an astronomical puzzle.
No, it's guaranteed to reveal physics beyond the standard model. It would be the first concrete evidence of particles and possibly forces that lie outside our current fundamental understanding. It would tell us where the standard model breaks down and point the way towards a deeper, more complete theory of nature. That's why the stakes are so incredibly high.
Okay, the stakes are huge. How are scientists actually trying to catch these particles? You mentioned experiments. Let's talk about the hunt. What are the main strategies?
Broadly speaking, there are three main experimental strategies for finding particle dark matter: direct detection, indirect detection, and production at colliders.
Let's start with colliders, like the Large Hadron Collider, the LHC.
Exactly. Places like the LHC smash particles, usually protons, together at extremely high energies. The idea is you convert energy into mass. If dark matter particles exist and have some interaction, even if very weak, with ordinary particles, you might be able to create them in these high-energy collisions.
But if they're invisible and weakly interacting, how would you know you made them?
You wouldn't see the dark matter particles themselves in the detectors. Instead, you look for their absence. Imagine a collision where particles fly out in all directions. If dark matter particles are produced and fly away without interacting, they carry energy and momentum away from the collision point without being detected. So scientists look for events with an apparent imbalance, missing energy or missing momentum that can't be explained by known particles escaping.
Like noticing something's missing from the picture.
Precisely. It's a very challenging signature to look for amidst the incredibly complex debris of proton-proton collisions. But experiments like ATLAS and CMS at the LHC are constantly searching for these kinds of events. So far, no unambiguous signal has been seen.
Okay, that's trying to make dark matter. What about catching it from space? That's direct detection.
Yes, direct detection aims to observe a dark matter particle, presumably from the halo of our own Milky Way galaxy, interacting directly with a detector here on Earth.
But you said they barely interact. How likely is that?
Extremely unlikely for any single dark matter particle. But the idea is that there are billions of them passing through us every second because the halo is all around us. So you build a detector with a very large mass of target material, make it incredibly sensitive, and shield it extremely well from all other sources of background radiation.
Where do you put these detectors?
Deep underground, often in mines or tunnels, sometimes under mountains. Examples include the LUX Zeppelin, LZE experiment in South Dakota, Xenon in Italy, Pandex-4T in China. Going deep underground shields the detector from cosmic rays coming from space, which could easily mimic a dark matter signal.
And what are they looking for inside the detector?
They're looking for that very rare event where a dark matter particle, like a WIMP, happens to collide with an atomic nucleus in the detector material, often something heavy, like liquid xenon or germanium crystals. This collision would cause the nucleus to recoil, creating a tiny flash of light, scintillation, or a small electrical charge, ionization, that sensitive instruments can pick up.
A tiny, tiny signal.
Incredibly tiny. That's why the detectors need to be ultra-pure, ultra-sensitive, and shielded like crazy. It's an extraordinary technological challenge. And again, despite pushing the sensitivity limits lower and lower over the years, these experiments haven't yet found a confirmed dark matter signal. They've ruled out many theoretical models, particularly for simpler WIMP candidates, but haven't made a discovery.
Okay, so making it at colliders, catching it directly underground. What's the third approach? Indirect detection.
Indirect detection takes a different tack. Instead of looking for the dark matter particle itself, it looks for the products of dark matter annihilation or decay.
Annihilation, like matter-antimatter.
Possibly. If dark matter particles are their own antiparticles, as some theories suggest, or if there are equal amounts of dark matter and anti-dark matter, they could collide and annihilate each other, especially in regions where dark matter is expected to be very dense, like the center of our galaxy or in nearby dwarf galaxies.
And what would this annihilation produce?
It would likely produce a shower of standard model particles, things we can detect, like high-energy gamma rays, neutrinos, or even antimatter particles like positrons or antiprotons.
So you look for an excess of these particles coming from regions where dark matter should be concentrated.
Exactly. Telescopes like the Fermi Gamma Ray Space Telescope scan the skies for gamma rays. Neutrino detectors like IceCube at the South Pole look for high-energy neutrinos, and experiments like the Alpha Magnetic Spectrometer, AMS, on the International Space Station look for cosmic ray antimatter. They search for signals that have the specific energy signature or spatial distribution expected from dark matter annihilation or decay above the known astrophysical backgrounds.
Any luck there?
There have been some intriguing hints and anomalies over the years. For example, an excess of gamma rays observed from the galactic center by Fermi, and some unexpected results from AMS. But so far, none of these signals can be definitively attributed to dark matter. There are often plausible astrophysical explanations, like pulsars or other cosmic phenomena, that could also produce similar signals. So the jury is still very much out on indirect detection as well.
So across the board, colliders, direct detection, indirect detection, the hunt is intense, the technology is incredible, but no definitive catch yet.
That's the current status. It highlights just how elusive this stuff really is. It either interacts even more weakly than we thought, or perhaps it's something entirely different like axions requiring different search strategies, or maybe our whole approach needs rethinking.
Which brings up an interesting point. We've been assuming dark matter is some kind of new particle, but what if? What if the problem isn't missing matter, but our understanding of gravity itself? Could gravity work differently on large scales?
That's a very important alternative perspective to consider, and scientists have definitely explored it. If gravity behaves differently than predicted by Newton or Einstein under certain conditions, maybe you wouldn't need dark matter to explain the observations.
What's the main theory in that camp?
The most well-known alternative theory is called MOND, which stands for Modified Newtonian Dynamics. It was proposed by Mordechai Milgram back in the 1980s.
And what does MOND suggest?
MOND's core idea is that Newton's law of gravity, or perhaps Einstein's general relativity, needs a modification, but only under specific circumstances, namely in regions of extremely low acceleration, like the kind experienced by stars in the far outer edges of galaxies where the gravitational pull is very weak.
So where gravity is weak, it doesn't fall off as quickly as we expect. It's slightly stronger.
Essentially, yes. MOND proposes that below a certain tiny threshold of acceleration, the effective gravitational force becomes stronger than the standard prediction. If this were true, it could potentially explain why stars in the outer parts of galaxies orbit faster than expected. They're feeling a stronger gravitational pull than Newton would predict based on the visible mass alone. so you wouldn't need extra dark matter mass.
That sounds elegant, actually. No need for exotic new particles. Does it work?
It works remarkably well for explaining galaxy rotation curves, often with fewer free parameters than dark matter models require for individual galaxies. That's its main strength.
There's always a but, isn't there?
There usually is in science. While MONE is successful on galactic scales, it runs into significant problems when you try to apply it to larger structures, like galaxy clusters. The amount of missing mass inferred in clusters, for instance from gravitational lensing or the motions of galaxies within the cluster, is much larger than what MONE typically predicts. It doesn't seem to provide enough extra gravity on those scales.
So it works for galaxies but not clusters.
Generally, yes, it struggles with clusters. And perhaps the most damning evidence against simple MOND comes from systems like the bullet cluster.
Right, you mentioned that before, the colliding clusters.
Yes, in the bullet cluster, we see two galaxy clusters that have passed through each other. The ordinary matter, mostly hot gas, collided and slowed down, and we see it concentrated in the middle using X-ray telescopes. But the gravitational lensing map, which traces the total mass, shows that most of the mass didn't slow down. It passed right through, just like the galaxies did. The mass peaks are separated from the gas peaks.
Which is exactly what you'd expect if most of the mass is collisionless dark matter, but not if gravity itself is modified, right? Because MOND ties gravity to the visible matter.
Precisely. MOND generally predicts that gravity should be strongest, where the ordinary matter, the gas in this case, is most concentrated. The bullet cluster shows a clear separation between where the gravity is strongest, lensing peaks, and where most of the ordinary matter is, gas. This is very hard for MOND to explain naturally, but it's a slam-dunk prediction of the standard dark matter model.
And what about the cosmic microwave background? Can MOND explain that?
That's another major hurdle. Explaining the precise pattern of fluctuations in the CMB requires physics that operates in the very early universe, long before galaxies and clusters formed. Standard MOND doesn't have a well-developed cosmological model that can naturally reproduce the CMB power spectrum with the same precision as the lambda CDM model, the standard model with dark energy and cold dark matter. Relativistic versions of MOND exist, but they often struggle to fit all the cosmological data simultaneously.
So while MOND is an interesting idea and works well in some specific cases, it doesn't seem to provide the comprehensive explanation across all scales that dark matter does.
That's the general consensus in the field right now. The standard lambda CDM model, despite the unknown nature of dark matter and dark energy, provides a remarkably consistent and successful framework for explaining a vast range of observations, from the early universe, CMB, to galaxy rotation curves, to gravitational lensing, and large-scale structure. MOND and other modified gravity theories haven't yet achieved that level of comprehensive success, though research continues.
Okay, sticking with the standard picture then, we have this 27% dark matter and this 68% dark energy. They're both dark, both mysterious. Do we know if they interact with each other? Are they connected somehow beyond just being the dominant components?
That's another frontier question. Their exact relationship and potential interactions are still unclear. In the standard lambda CDM model, they are usually treated as separate components that don't interact directly, other than through their gravitational influence on the expansion of spacetime. Dark matter's gravity tries to pull things together and slow down expansion, while dark energy effectively pushes things apart and accelerates expansion.
So they're kind of in a cosmic tug of war over the fate of the universe.
You could definitely see it that way. Early in the universe, matter, both dark and ordinary, was denser, and its gravity dominated, slowing down the initial expansion. But as the universe expanded, the matter density decreased, while the density of dark energy seems to remain constant. Nearly so. Eventually, dark energy became dominant, a few billion years ago, and started causing the expansion to accelerate, which is what we observe today.
Could they interact in other ways? Could dark matter decay into dark energy or vice versa?
People definitely explore theoretical models where dark matter and dark energy do interact in non-gravitational ways. This is often called interacting dark energy or coupled quintessence. These models are interesting because they might help alleviate some tensions or coincidences in the standard model, but there's currently no strong observational evidence favoring such interactions. It remains an area of active theoretical research. For now, the simplest model, where they only interact gravitationally, fits the data pretty well.
So, another mystery layered on top of the others. The universe's unseen majority remains deeply enigmatic.
It certainly does, that 95%. It just underscores how much we still have to learn about the fundamental workings of the cosmos.
So looking ahead, what's next in this cosmic detective story? How are scientists planning to push the boundaries further? You mentioned the Vera Rubin Observatory.
Yes, the Vera C. Rubin Observatory is going to be a game changer for mapping dark matter through gravitational lensing. Its Legacy Survey of Space and Time, LSST, will provide unprecedented data on the distribution of dark matter on large scales, allowing for much more precise tests of cosmological models and dark matter properties. By observing how dark matter clumps over cosmic time, we can learn more about its nature. For example, is it perfectly cold, or does it have some small velocity that affects structure formation?
So, better maps, more detailed understanding of its distribution.
Exactly. And other upcoming telescopes, both ground-based, like the Euclid Space Telescope and future space missions, will also contribute significantly to mapping the cosmic web and probing dark matter and dark energy through various techniques, including lensing and galaxy clustering.
What about the direct search? Are the underground experiments reaching their limits, or is there hope for the next generation?
They're definitely not giving up.
Yeah.
The next generation of direct detection experiments, like the proposed Darwin Observatory, which would use tons of liquid xenon, aim to push sensitivity down much further, probing deeper into the theoretically predicted parameter space for WIMPs, and potentially becoming sensitive to other types of interactions or even solar neutrinos. Similarly, axion searches are rapidly evolving with new technologies and ideas. The hope is that with greater sensitivity and perhaps novel techniques, we might finally get that definitive signal.
And collider searches.
The LHC will continue its high luminosity phase, collecting much more data, which increases the chances of spotting rare processes, including potential dark matter production signals. And physicists are already planning for future, even more powerful colliders that could potentially open up new energy frontiers where dark matter might be hiding.
So the hunt continues on all fronts, pushing technology and our understanding. But for now, what are the biggest unresolved questions? What keeps cosmologists and particle physicists up at night when they think about dark matter?
Well, the absolute biggest one is still, what is it? What particle or particles make up dark matter? That's the fundamental question.
The composition.
Right. Beyond that, how does it interact, if at all, with ordinary matter beyond gravity? Does it interact with itself? Does it have its own complex dark sector physics? What are its precise properties, its mass, its spin? And what is its exact role in cosmology?
Yeah.
How did it shape the very first stars and galaxies? How does it relate to dark energy? These are all major open questions.
So until we get that direct detection or maybe some completely unexpected theoretical breakthrough?
Exactly. Until then, dark matter remains one of the most profound and motivating unsolved puzzles in all of science. It's not a dead end, though. It's a sign that there's incredibly exciting physics waiting to be discovered, physics that lies beyond our current understanding. Every null result from an experiment is still valuable information, helping us narrow down the possibilities and refine our search.
It's a fascinating state of affairs. We've journeyed through this enigma, starting with just the concept of something invisible shaping the universe.
Yeah, from its sheer abundance, that staggering 27% compared to our 5% to the concrete evidence.
Right, the galaxy spinning too fast, the light being bent by unseen mass and clusters, those incredibly precise patterns in the cosmic microwave background, all pointing towards its existence.
And we explored the candidates, the long-favored WIMPs, the well-motivated axions, other possibilities, all highlighting that this is physics beyond the standard model.
And the incredible ingenuity of the experiments trying to find it, smashing particles at the LHC, listening for tiny whispers deep underground with experiments like LUX Zeppelin, scanning the skies for annihilation signals.
Even considering the alternatives like MOND, and seeing how they stack up against the full range of evidence, and realizing that dark matter, along with dark energy, makes up that astonishing 95% of the universe.
Leaving us with the ongoing quest, using next-gen telescopes like Vera Rubin to map its influence even better. The core mystery, its composition, its interactions remains, driving future research.
It really is a testament to human curiosity, isn't it? That we can infer the existence of something so pervasive, so fundamental, even when it hides itself so completely from our direct senses.
It absolutely forces us to think beyond the familiar, beyond what we can immediately see or touch. It expands our definition of what reality might encompass.
Exactly. And maybe that's the final thought to leave people with. If dark matter shapes the entire cosmos, providing the scaffolding for galaxies like our own, and yet it remains utterly invisible and intangible to us, what does that really tell us about the limits of our own perception?
Yeah.
What else might be out there, fundamentally shaping our reality, operating by rules we haven't even begun to decipher yet? It suggests the universe is far stranger and far richer than we probably imagine. The search for dark matter isn't just about finding a particle, it's about understanding our true place in this vast, mysterious cosmos.
A truly